All right, welcome guys. So today we're going to talk about using the power series method to solve linear ODEs. And we're going to we want to talk about this method to solve linear ODEs that have, in particular, variable coefficients, right? Um, so what I first want to just refresh your memory on, I'm not going to write anything, too crazy out for this, but when I say a power series, I just mean something that looks like this. Oh, I don't know what happened there. So let's go back up and let's undo that. Oops, I guess I'm undoing too much now. All right, well, let's go back up here. Okay, let's see, can I erase that? Yeah, okay. All right, so when I say power series, I just mean something that looks like this, right? So you have, this is, in particular, is the power series centered at the point x0. And then we just have sort of our coefficients, which we call a0 through, as big as you like, a infinity, so to speak. And of course, those are constants, right? Now, whatever point is here inside each of these differences, that is said to be the center of your power series, right? So these are all centered at x0. Right, so a common choice for x0 is when x0 is 0 itself, right? So then, in particular, we have something that looks like this. So we have a0 plus a1 times x plus a2 times x squared, so on and so forth, right? And you can sort of take this out as big as you like. Now, so you're probably familiar with some of these power series. So in particular, the first one, if you have 1 over 1 minus x, that's your geometric series, right? Right, and of course you need your absolute value of x to be less than 1 if you want this thing to converge, right? And then you have your series for e to the x, which essentially is just going to involve some factorials in your denominator. And then you have your cosine and sine, which are sort of like the even and the odd powers of your e to the x series. And then, of course, they alternate, right? So those are just some sort of review topics as far as power series go. Now, what we want to do is, using a power series method, we want to be able to solve ODEs, right? So the first one that I want to look at is y prime minus y is equal to 0, right? Now, of course, you could do this by separation of variables, right? If you let y prime, if you were to let that just be dy dx, dx, then you can move your dx over to the other side and you'd arrive at this. And once you divide both sides by y, and then of course you could integrate both sides and then exponentiate, and then of course you end up with e to the x times some constant, and which for the moment I'm just going to call that constant a0, right? And hopefully that will sort of be for obvious reasons at this point, right? So the idea is that we can solve that ODE very easily with separation of variables, but I want to go through what this looks like by using the power series method. All right, so what we're going to do is we're going to assume that the solution y is some power series. So we're going to assume that it's a0 plus a1 times x plus a2 times x squared, and so on and so forth, right? Or if you want to write this in summation notation, we could say that this is the sum, as m goes from 0 to infinity, of a sub m times x to the m, right? Now, if we use this convention, then y prime, right, with respect to x, of course, so a0 drops out, and we're going to be left with a1, right? Because if we take the derivative of a1x, we just get a1. And then we'll have a 2 a2 x, that's now just to the first power. And then we get a 3x squared, and so on and so forth. Right? Now, the advantage here of the summation notation is that you could have found this by just differentiating the arbitrary term, right? So what would you do? You'd multiply each number by m, and then you have your a sub m from before, and then you drop your power of x by 1, right? So that's essentially what we have, right? Now, again, remember that our original ODE that we want to solve was y minus y prime is equal to 0. So now that we have both of these expansions, these power series expansions for each of these, let's write out what we have. So we have a0 plus a1 times x plus a2 times x squared plus so on and so forth. And then we're subtracting y prime, which is a1 plus 2a2 times x plus 3a3 times x squared, and so on and so forth. And this is equal to 0, right? So again, where did these things come from? This was the power series expansion for y. This was the power series expansion for y prime. Right? Well, now what we can do is we can equate coefficients. Right? So if we look at our constant terms, we have a0 minus a1. Right? Those are just the first terms in each of those power series. Right? Then plus, what are my x terms? I have a1 minus 2a2 times x. And then we have plus a2 minus 3a3 times x squared, and so on and so forth. Right? Now, if this is going to equal 0, then I need each of these things to equal 0. So I would need a0 minus a1 to equal 0. I would need a1 minus 2a2 to equal 0. I would need a2 minus 3a3 to equal 0, and so on and so forth. All right, so I need these to be true. To be true. Right, so the standard sort of convention for this is now we solve everything in terms of a0. Right, so if I solve the first one, I bring this over here, and we solve that for a0, or if we solve a1 for a0, I should say, in terms of a0, we get that a0 is equal to a1, right? Then in the next equation, let's use blue. In the second equation, right, we just said that a1 was a0, so I'm going to plug that in, and we're going to have that a0 minus 2a2 is equal to 0. So then I get that a2 is equal to a0 over 2. All right, so that's what a2 is. And then in the last one, at least the last one that we have written out here, we have that a2, which we just said was a0 over 2. I should get rid of that. Looks like a negative. Okay, so we have a0 over 2 minus 3a3 is equal to 0. So if we solve this, we'll get a3 is equal to a0 divided by a 6. Or for our sake, you might want to think of that as a 3 factorial, right? So once you do enough of these, and sort of if you don't see the pattern right away, the idea is that you just sort of, you keep going until you see the pattern. But we can say that in general, the kth coefficient is just going to be a0 over k factorial, right? So if you look at A1, that's just A0. If you look at A2, that's A0 divided by 2, which is also 2 factorial. And then A3 is A0 divided by 6, which is also 3 factorial, right? And of course, that lines up with what we have, because now if we write out what our y is, we said that y we assumed was A0 plus A1 times x plus A2 times x squared, so on and so forth. And if we plug in what we have, well, we have this is A0. We said that A1 was just A0. And we said that A2 was A0 over 2 times x squared. And the next one, I might as well say it since we did the work for it, is an A0 divided by 3 factorial x to the third. Now, of course, we can factor out an A0. So then we have x squared over 2 factorial was x to the third over 3 factorial, and so on and so forth. Now, of course, what is this power series in the parentheses here? That's just e to the x, right, which is what we expect. And then, of course, A0 is just along for the ride, and that's what our solution should come out to be, right? So we get the same answer, of course, not surprisingly, that we did with separation of variables as we did by using the power series expansion, right? So that's sort of what we are looking to do with this method, right? Now, that's a very particular case, but we can sort of apply the same logic so for the general case, right? So in general, of course, what we want to do is we want to write our ODE in this form, right? So we want to have something that looks like this form. And similarly to when we looked at linear ODEs, you know, if there was something in front of that y double prime, you just divide everything by whatever that something is, and then you arrive at an equation of this form, right? Now, of course, you would want to represent this px and this q of x. You would want the power series version of those things, right? And of course, if they're polynomials, then you don't need to do anything, right? Because the polynomial is already sort of in power series form, and then at a certain point, it's the rest of its coefficients are just zeros, right? So then, just like we did before, we would assume that y is that power series that we had before, and then y prime would be the other power series. And then for y double prime, you just do a little bit more work. I'm cutting off this here. But you do a little bit more work, and you'd find that that's what your power series expansion for y double prime is, right? And then you equate your coefficients. And if you solve each equation, you can then find, hopefully, a pattern for the arbitrary coefficient, and then you can determine what your solution is. All right. So let's do a little bit more of an interesting example. All right. So we're going to look at this equation where we have 1 minus x squared times y double prime minus 2x times y prime plus 2y is equal to 0. Now, again, this sort of ODE is not quite in this form, but again, of course, the idea is that you could divide through, in this case, by 1 minus x squared, and you could get something that's in the form that you want. All right, but I actually want to leave the ODE like this because it'll be a little bit easier to solve it. All right, so again, what do? We assume that y is equal to a0 plus a1 times x plus a2 times x squared, so on and so forth. And then we get that our y prime is a1 plus 2a2x plus 3a3x squared. And then y double prime would be 2a2 plus a6 A3x. And then let's see, I guess I would need a plus, plus a 12, A4x squared, right? And so on and so forth. Okay, so now I want to plug each of these expressions in for these three things in my original ODE, right? So of course I need to do 1 minus x squared times my power series for y double prime, 6a3x plus 12a4x squared, so on and so forth, right? And then I'm subtracting 2x times my power series expansion for y prime, which is a1, plus 2a2x plus 3a3x squared, and then plus 2 times my power series for y, and of course all of this is just equal to 0, right? So now we need a little bit of algebra here, right? So I guess if we look at our first series, we could say that we have a 2a2. I'm just going to multiply everything through by the 1 first. So we get a 2a2 plus a 6a3x plus a 12a4x squared, so on and so forth. If I multiply through by the negative x squared, I'm going to get a minus 2a2x squared, and then a minus 12a3x to the third, and a minus 12a4x to the fourth, so on and so forth, right? And then if I go to multiply the next one, right, if I concentrate on this now, I'm going to get a minus 2a1x minus a 4a2x squared, and a minus 6a3x to the third, and so on and so forth. And then finally, let's see, how about that? Sure. And then in the last one, we'll get a 2a0 plus a 2a1x plus a 2a2x squared plus so on and so forth. All right. Now, if we combine our like terms here, let me come up here, and we equate our coefficients, we get the following equations here, right? So for a constant term, we need everything to be equal to 0. So we get a 2a2 plus 2 times a0, that better equals 0, right? So if I look here, I would just want to combine these two terms, and I would want them to equal 0, right? For my x term, we need 6a3 minus 2a1 plus 2a1 to equal 0. All right, for my x squared, you can eventually find, and you should verify on your own, that you would get that 12a4 minus 4a2 is equal to 0. And then x to the third, you can eventually show that a5 is equal to 0. And for x to the fourth, you would get that a6 is equal to negative 1/5 a0. Right? So now we would just need to solve the rest of the ones that I didn't sort of have in my back pocket here. We just need to solve them in terms of a0. and that's fine, right? So in this one, we get that A2 is a negative A0. If we solve the x equation, we would eventually find, right, because these two are going to cancel, we would get that A3 is equal to 0. If I solve the x squared equation, we're going to eventually get that A4 is equal to negative 1/3 A0. And here's what we run into, right? So it looks like our odd coefficients will disappear since we get 1, 3, and 5 all have to be 0. And then our even ones look like we are, getting something obviously non-zero there, right? So now what happens? Well, now we can say that our solution is y is equal to, sorry, our A1 is not necessarily 0. It's sort of a free choice, right? So it's A1 times X, right? Because I didn't get any explicit description for what A1 would need to be. So we actually get a free choice there. But then the rest of this will look something like plus A0 times 1 minus x squared, once we fill in all these coefficients, plus 1/3 x to the 4th minus a 1/5 x to the 6th, and so on and so forth. So there's our solution. Right, and this is actually a special form here. This is what's known as, I'm not going to know if I'm pronouncing this right, but this is Legendre polynomials. Right, so you actually have here that P1 of x is just x, and then you have that negative Q1 of x is the other stuff, right? So that's the 1 minus x squared plus 1/3 x to the 4th minus 1/5 x to the 6th. And maybe in a future video, we'll talk a little bit more about that, but that's just sort of an interesting fact here. All right. Now, I do want to spend a little bit of time to talk about sort of the theory as to why this works. So we'll go through that quickly, and then we'll wrap this video up. All right. So the theory as to why this works basically revolves around the fact that we're looking at the partial sums, right? So any partial series, any power series can be broken into its nth partial sum by just taking the first n terms. And then the remainder is just whatever comes after it, right? So this is like the remainder of your nth partial sum, because it's everything after the nth term, right? So then there's a couple of little examples here that just show that if you're looking at, for example, the geometric series, that would be how the breakdown of the nth partial sum and the remainder looks like, right? Now, the idea behind why this method works is that if you have some partial sum converge, right, then we say that the series is convergent, right? So whatever value of x makes that series convergent, we say that it's convergent at that x value, right? And we say the value or the sum of the series is just given by whatever that nth partial sum is converging to, right? Now, of course, if it diverges, then we just say that the series is divergent, right? Now, when you have a convergent series, there's basically what you can say is that for any number that's as small as you like, you can essentially make your remainder as small as you want, right? Because if the series is converging to some value, then that means that your remainder better be getting smaller and smaller. Otherwise, you're not converging to anything, right? So that's sort of what this is saying right here. Right. So now you have sort of a geometric description here of where does a power series converge, right? So now we chose that we had an x1, for example, in in this sort of definition here, x1 was a specific x value. All right, but it turns out that you might not have convergence only for one specific x value. It might be for more than one, right? Or it might be for an infinite number of x values, right? Now, we know that the series is going to converge in usually some interval, right? So for some particular radius of convergence, right, the distance between x, which is just the arbitrary x value, and then x0 is a known convergence x value. Then if the arbitrary x value still converges, then it better be within some fixed radius, right? So that radius r is what we're going to call, right? And you see sort of like the geometric idea here is that for some r value, you have convergence, and then outside of that r value, you no longer have the convergence, right? So we usually call that r value the radius of convergence. Right, and you can show sort of how to find this radius of convergence using some techniques from complex analysis, but we won't go into that detail in this video. And you can find the radius of convergence by just looking at the limit of your mth root as m goes to infinity of your coefficients, right? So you can find your radius of convergence by looking at what happens to your coefficients as you go out to infinity, right? So now a couple things that you might notice are that if you're, so let's make a little note here, right? So if these limits go to infinity, well, then what's something like 1 over infinity? That means that your r is 0, and you only have convergence at a single point. If it converges at all, right? And then, of course, if the limits go to 0, that's sort of the other extreme, well, then your radius of convergence is infinite, and that's where you converge for all x. Right, so those are two sort of extreme cases here. But otherwise, if it's finite, you just compute whichever limit you desire, right? So probably in a Calc 2 or Calc 3 class, you would talk about how to evaluate these limits. For example, the nth root test or the ratio test is sort of what's going on here, right? So now, just to wrap this video up, we'll look at two examples as to how you can figure this out. Now, of course, the first power series that we'll look at is for e to the x, right? And we know that that converges for any x value, right? You plug in an x value, you get some number to come back out, right? Now, if you look at what's happening to all these coefficients, all your coefficients are factorials, right? So if you look at the ratio, you get a 1 over m plus 1, which as m goes to infinity goes to 0. So then that tells you that your radius of convergence is infinite. Now for the geometric series, 1 over 1 minus x, right, this one right here, we know that that has to that will only converge when the absolute value of x is bounded by 1, right? Of course, non-inclusive, right? So now if you look at these coefficients, right, they're all 1. So if you look at the mth ratio, you get 1 over 1, which is 1. So then that tells you radius of convergence is 1, right? Which makes sense because that's what we'd expect. Now, if you look at the power series where each coefficient is the factorial of whatever the power of x is, of course, that's going to grow without bound, right? Because if you look at that nth ratio, you get m plus 1, which, of course, is going to go to infinity. So that's not going to converge for any value of x unless, of course, your value of x is 0, right? So that's sort of, that wraps up this video on using the method of power series to test for, not to test for, but to find solutions of linear ODEs, right? So I hope you enjoyed the video, and I will see you next time.